Hello all, welcome to the second part of spatial filtering. So in first part we have discussed smoothing filters. So in that we have discussed linear filters and non-linear filters. In linear filters we have discussed the averaging filter, and in non-linear filters we have discussed the median filter. So now we will discuss the sharpening spatial filters. So in sharpening spatial filters, what do? We enhance the fine detail in an image, and in this we enhance the blurred images. So it actually in sharpening filtering, what do? We do opposite of the smoothing filters. So in smoothing filters we use the averaging. We use in linear smoothing filter we use averaging. So which we can say is analogous to integration. Averaging is analogous to integration. So sharpening can be achieved by spatial differentiation. So since we want to achieve the opposite of the smoothing filter in sharpening filters, so since we were doing averaging in the smoothing filter, which is analogous to integration, so in sharpening what we will try to achieve the differentiation. Now, the strength of differentiation is proportional to discontinuity of the image. So, if there is a change in the intensity level of the pixels, that would be the strength of the differentiation of that particular image. So, hence we can say that these sharpening filters will enhance the edges, and it will de-emphasize what slowly changing gray levels. It will de-emphasize the slowly changing gray levels. So it will work well for the edges, and it will de-emphasize the slowly changing gray levels. So if you remember, smoothing filters used to unintentionally smoothens the edges, which are actually the information carrying element in the images. So now carrying forward, we can have first order derivation and second order derivation for a discrete signal. One dimensional discrete signal, the first order derivation can be given as del f by del x, that is equal to fx plus 1 minus fx. That means the present instant is subtracted from the future instance. So that is how we get the first order derivative. The second order derivative we get by this formula, that is del 2f by del x square, that is equal to fx plus 1 plus fx minus 1 minus 2fx. That means the next instance and the previous instances are added, and 2 times of the present instance is subtracted from the resultant. So that is how we get the second order derivative of a function f. So hope this is clear to you. Now moving forward, suppose to look how we can apply these derivatives on image signals. Suppose this is an image of multiple objects in it. So here, if I take the intensity along this line over here, so here we can see that the gray level is varying. So it is slightly brighter, then it becomes darker, and here it is quite dark, and here we have a very small number of pixels which have the high intensity, then it becomes again dark. Then here we have a line which have little uh, brighter pixels than the darker, then we again get the darker pixels, and then here we have the white pixels or the brightest pixels. So if I draw the profile of the intensity level across this line, then it would be like this. So here we can observe that the intensity level is up to a mark, or it is not highest but it is close to the brightest level, and then the intensity is decreasing in the right hand side. So here we can see this curve is decreasing, then it becomes totally zero over here, so it becomes totally zero here. Then we get a pixel which has the brighter intensity than the black, quite brighter than the black. So here the intensity goes high and then comes back. Then again we have black here, so it represents black. Then here we have line, so it increases, and this line is of a very small width, so it increases here and then goes back to black. Then after certain distance, it becomes white, so it is totally white and it goes to the highest level here. In this region it is the highest level. So this is the profile of intensity levels along this line. Now if we want to represent it using the gray levels, then it would be like this. Here total 8 gray levels are chosen, 0 to 7. So here it has been mapped that this level is 5, this gray level is 5, and these brightest levels are 7. And accordingly here, since the intensity is decreasing, so it is shown by this decreasing ramp. Then it is 0, then it is a high intensity for a particular pixel, so we have got it here. Then again dark pixels are represented. Then we have an edge there, so that edge is represented by this. And then again dark line is there, dark area is there, so that is represented by 0 intensity values or the gray levels. And then the intensity increases to the brightest or the highest intensity value. So this is the profile in digital form along that particular line, along this line. So now if I write the intensity values along this line, then I can write, see, these two pixels have the intensity values 5, 5. Then since it is decreasing, so it is 4, 3, 2, 1, and then it becomes 0. For these three elements it is 0. Then at this particular pixel the intensity is 6, that is gray level is 6. Then again it becomes 0, and then it is 1, 3, 1, and so on. We can find the intensity of each particular pixel. Now if I want to take the first derivative of these intensities, so first derivative of, what is the formula for the first derivative? Fx plus 1 minus fx. That means the next instance, from the next instance we subtract the current instance. So for this particular value, the next instance is 4, so, and the current instance is 5, so 4 minus 5 is minus 1. So this is the first derivative corresponding to this value. Then next is 3 and the current is 4, so 3 minus 4 is minus 1 again. 2 minus 3 is again minus 1, 1 minus 2 is minus 1, 0 minus 1 is minus 0 minus 1 is minus 1, then 0 minus 0 is 0, 0 minus 0 is 0, 6 minus 0 is 6, then 0 minus 6 is minus 6, and so on. We can find out the first derivative. Then if we want to find the second derivative, then the formula is the next instance plus the previous instance minus 2 times the current instance. So let's check. So corresponding to this, the next instance is 4 and the previous instance is 5, so 4 plus 5 is 9 minus 2 times the current instance, that is 5, so 2 times of 5 is 10, so 9 minus 10 is minus 1, so we have got minus 1 here. The second derivative corresponding to this pixel is minus 1. For this, next instance is 4, previous instance is 5, so next instance is 3, previous is 5, so total is 8 minus 2 times the current instance, that is 4. So 2 times 4 is 8. 8 minus 8 is 0. So we have got it 0. Similarly, if we calculate the second derivative of this, then we get these numbers as the second derivative of these pixel intensities. Now, after finding out the first and second derivatives, we can deduce two outcomes from here. First is, if we look at the ramp's signal, so this is the ramp. So here intensities are continuously decaying. So if we observe the first derivative and the second derivative of the ramp, then the first derivative is constant. First derivative is constant all over the ramp, whereas the second derivative is non-zero only for setup and end point of the ramp signal. Setup, this is the setup point and this is the end point. So for only for these it is non-zero, and remaining it is 0. And if we look at this, then this is your step signal. That means it is suddenly changing from 0 to a particular brightest value. So we can say the first order has this strong effect for to the gray level step signal. So if it is first order derivative, it has the strong effect, whereas the second order derivative will have double response. You see, how can we say it is double response? It We get a positive number and then we get a negative number for a step. So if we take the second derivative of a step signal, I get a positive and then a negative, so we get a double response corresponding to that. So from here we can say, from the ramp signal first derivative and second derivative, we can deduce that first order derivative produces thick edges. So you see, the first order considers this whole as one edge. So this is your thick edge, and second order more finer edges. So the second order derivative will consider only this part and this part as the edge. So your second order derivative will detect the finer edges. So that is why we mainly focus on the second order derivative. Moving forward, now how can we utilize second order derivative in sharpening of the images or in the image enhancement? So for the image enhancement, what do we require? We require isotropic filters. What do I mean by isotropic filters? Isotropic filters are those filters which do not depend on the direction of discontinuities. What do I mean by this statement? I mean by this statement is that if I rotate the image in any direction with any angle, then too the output of the filter should be same. It should not change with the rotation of the image in a particular direction. So that we call isotropic filters. So we will get to understand this, that how we say these are the isotropic filters. Now how do we develop these isotropic filters? So the simplest derivation, isotropic derivation operator is Laplacian operator, and Laplacian operator is given by del square f, that is equal to del 2f by del x square plus del 2f by del y square. So since f represents an image which is two-dimensional signal, so when we take the partial derivative of f with respect to x and second order partial differentiation of f with respect to x and second order partial differentiation of f with respect to y, and when we add these two, we call this as Laplacian operator. Now from the second order differential uh, derivative, second order derivative formula, if you remember, this one. So here what do we do? The second order derivative, the next instance and the previous instances are added and the current instance is subtracted. Two times of the current instance is subtracted. So from this formula, if I write this del 2 f by del x square, that would be equal to f x plus 1 y, that means it is the next instance, f x minus 1 y, that means it is previous instance, so these two are added, and minus 2 times the current instance, that is f x y. So we can write f del 2 f by del 2x square will be equal to this. Now similarly we can write del 2f by del 2y square, that is equal to f x y plus 1, that is future instance, f x y minus 1, that is the previous instance, and f x y is the current instance. So two times of this is subtracted. Now if I want to write this del square, that is Laplacian operator, that is equal to summation of these two. So if I write summation of these two, this will be f x plus 1 y, f x minus 1 y, then f x plus x y plus 1 plus f x y minus 1, this term as it is, then two times f x y here and two times f x y here, so it will be minus 4 times f x y. So this is the result of Laplacian operator applied on an image. Now if I want to deduce the filter coefficients from this equation, then if you remember the filter coefficient, how did we apply the filter on the image? So what do we do? The filter coefficients are multiplied by the coinciding pixel intensities, right? So and we know that fxy is the pixel intensity which is coinciding with the center pixel. So minus 4 would be the weight of center pixel of the filter or the mask. So you see here we can say minus 4 would be the coefficient of center uh, element of the filter. And then you see, if I say this, if the center is here, that is xy, that represents xy, then x plus 1 y would be fx plus 1, that means next row, and y is same column, so this will be this. So these four values represents the orthogonal elements of this filter. So orthogonal elements are 1 and diagonal elements are 0. So this is how we can get a mask or a filter from this equation. So now if I apply this mask on an image, then what would happen? Suppose this is your fxy, so it would be fx y plus 1, it would be fx y minus 1, this would be fx minus 1 y, it would be fx plus 1 y. So they all will be multiplied and added together, so we will get this expression. So this is how we implement the Laplacian operator on an image. And then we know that the filter is slided all over the image pixels in x direction and y direction. Now this pixel is isotropic with incremental angle of 90 degree. What do I mean by incremental angle of 90 degree? That means if I rotate the image by 90 degree, the result will still be same. Why? Because you see here orthogonal coefficients have the same value. So even if I rotate it by 90 degree, I will get the same filter again. So it has the uh, isotropic nature with the angle, incremental angle 90 degree. Now if I consider the diagonal pixels too, so here you see along with these four orthogonal pixels, I have added the diagonal pixels too. So when I am adding diagonal pixels, I have to subtract this current pixel four times more. So I get the center pixel coefficient as -1, and remaining these pixel coefficient will be 1 1 1 1. So this is the uh, Laplacian filter with 45-degree incremental angle. Now these masks, these filters can also be implemented by using this method. That means your center pixel center coefficient is positive and remaining coefficients are negative. So here the center pixel was center coefficient was negative and remaining are positive. Here we can have a center pixel positive and remaining are negative. Same, this also we can implement like this. So this is how we can implement Laplacian operator on using filters on images. Now how do we actually enhance images using the Laplacian filter is, if I add, so what actually we get out of Laplacian filter. So Laplacian filter is our second order derivative, right? Second order derivative, what does it give? It gives us fine edges or fine information it gives us. So when we get the finer information, and that finer information is added with the original image. So this here we have got the finer information, and this is our original image. If I add this into the original image, I get the enhanced image. Now here you see we have two formula. If the center coefficient is minus negative, then in that case the fxy will have this minus sign after this. That means fxy minus del square fxy. And if center coefficient is positive, then fxy plus del square fxy would be the enhanced image. Now let's see how these Laplacian filters are applied on the images. So this is the image of north pole of moon. Now if the second order Laplacian filter is applied on this, then we get this kind of image. So here you see the edges are clearly visible. Edges are clearly visible, but since here we have a step response from dark to white, so it is a step response, so we have got double response here, double response in the output. Now if I want to see this image a little properly, then what do? I scale this image. Scaling means what? A constant value of gray level is added to all the pixel intensities. So that is scaling. So after scaling, this image would look like this. And this image is enhanced image using Laplacian filter. That means when we add these two images, we get this enhanced image. So here now you can clearly see here the details are clearly visible, and here you can identify the edge very properly, and you can identify the regions very properly, which are not clearly visible in this original image. So this is how we can use Laplacian filters in the image enhancement. Now next, if I want to have filter coefficients which will directly enhance my image, so for image enhancement, what do? We add the Laplacian filter output into the original image. So this is fxy, that is original image. So if center pixel is negative, that means it is -4. So in that case we subtract it from the original image. So -4 will become +4 and these all coefficients will be negative. So minus here, this is into the bracket, and that minus and this minus multiplication will be plus. So here 4 fxy we get. So this 4 fxy and this fxy we get total 5 fxy, and minus all these coefficients, all these are coefficients. Now if I want to write filter coefficients corresponding to this equation, then you see the fxy is the coefficient, the multiplier of fxy is considered as center coefficient. So fxy has the coefficient 5, so this is the center coefficient. So this is center coefficient, and this fx plus 1 y, that means fx plus 1 y is -1, so this has -1. Similarly we have got these orthogonal coefficients which are -1, -1, -1. So when it is 5 and remaining are -1, then it is the filter which will directly enhance the image. It is not the Laplacian filter, it is the filter which will enhance the image, and this filter is called composite mask. This mask is called composite mask, so or composite Laplacian mask. So and if we want to include the diagonal pixels too, then instead of 8 we will have the number 9 here. Why? Because the original image is added into the Laplacian filter output. So here the composite mask will have these coefficients. So this is our original image, this is our original image. This is enhanced image using the composite masks or composite Laplacian masks, and this is enhanced by using this composite mask which does not include the diagonal elements, and here we can see that these lines which are at 45-degree angle, they are not perfectly enhanced, but here in this image we can see which the lines which are at the 45-degree angles, they are also very perfectly enhanced and they are perfectly visible in the output. Okay, so that's it about the sharpening filters. We'll meet in the next lecture. Thank you.